Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 4.3, and as you may recall, what we did in Module 2 is obtain this set of equations, this Valet-Fert equation or spin diffusion equations, and these are a lot like the usual diffusion equation. You see, the usual diffusion equation would be current is equal to minus sigma A divided by Q d mu dz. That is, current is proportional to the gradient of the electrochemical potential. And when you're doing things in one dimension, we know that di dz should be 0. So that's the usual thing. And if you need a reference, I guess you could look at this in the lecture notes. It's in the part 1 section. So it would be in like lecture 6 of the notes. Now, if we combine those two, you can see that di dz, that is, if I take the derivative of this, you would get, assuming conductivity doesn't vary spatially, what you'd do is pick up d2 mu dz2. And so, d2 second derivative of mu with respect to z would be 0. So that's the ordinary diffusion. And in a way, what we did in the last module is we said, well, we have these two types of spins. This red and blue are up and down. And it's as if there is a separate potential for the ups and one for the downs, and each one is equal to 0. That is, each one would be equal to 0 if they were completely independent. But what we discussed is they're not independent in the sense ups can convert to downs. So if you have a lot more ups than downs, there's always spin flip processes that try to turn one into the other. And that's what gives rise to this non-zero value for d2 mu dz2. Now, one of the very powerful concepts here that's widely used is that instead of working with up and down, you can define two quantities which you could call charge and spin. And the charge is like the sum of up and down. So if you're looking at current, you'd look at the up current and the down current, add it up, and you'd call that the total current, the charge current, the usual one we talk about. On the other hand, if you looked at their difference, that's what you'd call the spin current. And the same with potentials, see? And one way to think about this, why when you add it, it's charge, and when you subtract it, it's spin, one way to think about that is something like this. You see, you could say that, well, when you look at an electron, if it's a red electron or a blue electron, doesn't matter, whichever it is, they both have exactly the same charge. Each one is minus q. So if you had red electrons like 20 per second and blue electrons that were, let's say, 10 per second, that were flowing at 10 per second, then the total rate at which charge is flowing would be 30 per second because they both carry the same charge. On the other hand, when you think of spin, that's a different property which actually is different for red and blue. You know, spin you could think as a measure of, say, the redness of something. So for red, let's say the spin is plus s, and for the blue, the spin would then be like minus s. So what that means is you have 20 per second of plus s flowing and 10 per second of minus s. So the rate at which this spin or this redness is flowing is like the difference of the two. So it's like 10 per second. So this is the important sort of transformation, as a mathematician might call it, that one needs to be clear about. That you can think in terms of up and down, or you can look at the sum of the two, call it charge, look at the difference of the two, call it spin. Right? Call it the net spin. And these diffusion equations, when you write it in terms of charge and spin, have this nice property of decoupling. What I mean by that is, here you see up depends on up and down depends on up and down. So up and down are all kind of mixed up. Whereas here, I got two separate equations. So one for charge, one for spin. And for charge, the equation I have, you see, looks exactly like the ordinary differential in the ordinary diffusion equation. So what it means is if I'm looking at the charge potential, everything will look pretty much like I'm used to, as if I'd never heard of spin. On the other hand, when I'm looking at the spin potential, that's where we have a different equation, in the sense the derivative of this is not equal to 0, but is equal to mu s divided by this lambda square. And that lambda is what you call the spin flip length. And one thing that I should remind you about this differential equation is that the solutions to this equation, which would be useful, which we'll be drawing on, look something like this. That whenever you have this d2 mu s dz2 is proportional to mu s itself. So the solution to this can be written in the form of either e to the power minus z over lambda sf or e to the power plus z over lambda sf. This will satisfy that equation, and this will also satisfy that equation. So in general, you can write solutions in the form of some constant times this plus some other constant times this. And the way you figure out the constants is by applying the boundary conditions. So for example, if you are dealing with a problem where z goes off to positive infinity, then you expect that you should not have any term of this form, because it would blow up. You expect the solutions to die out, and so you'd only use that equation. But in other problems, I mean, this is what we'll be using in the rest of the lecture today, but in general, you might need both. Okay. Now, in order to illustrate how we think about spin potentials, and more importantly, how you actually measure them, because one of the things I've always stressed that one thing is very important is about these concepts is how you relate it to real experiments. See? Now, in terms of understanding spin potentials, measuring them, there is a class of experiments that are really very useful. These experiments are not, at this time at least, still not terribly important from the point of view of actual real device applications, in the sense that it's not like they let you do some particular useful function. On the other hand, they allow you to measure these quantities and get a lot of information about spins and how they behave in solids. So this is the kind of experiment we'll be talking about, and they look something like this. So let me explain the experiment I have in mind. You see, we talked about these two contacts, and there is these two channels that I have schematically shown as red and blue. And of course, as I mentioned, this is just schematic. It's not like red is on the top and blue is at the bottom. It's like they're everywhere. But conceptually, what I mean is there's two types of channels there. One for the reds and one for the blues. And let us say this is actually a magnet which says pointing in some direction up. And for this discussion, we'll assume that this one is just an ordinary contact, which contacts both of them equally. Problem. Now the part where we'll think of something a little different than what we have been talking about is that we'll assume that this is a short magnet and these channels kind of extend out beyond this contact, way out here. See? So when you look out here, you'd see this channel extend out. And now if you consider what the potentials will look like inside the channel. So let's first think about just the total potential. As I said, there is these two things, mu, which is mu up, plus mu down, divided by 2, that's the average. And then there is the spin potential, which is mu up minus mu down. So let's first think of the charge potential. Now the charge potential, of course, as you know, this obeys the basic equation, d2 mu dz2 equals 0. And when the second derivative of something is 0, means that it's basically a straight line. And so what you'd expect is somewhere around from here to the other end, it would be like a straight line. So if you think of this as our reference, which we call 0, then it will change linearly to some value here. And on this side, then it will again be flat at some value. Now, let me lower that a little bit. So I have some room here. So that's what the charge potential would look like. Now, what is the value here? Well, that depends on the interface resistance, because the current, you see, comes in from here. This electron current comes in and has to go through the interface resistance in order to reach the channel. So there is a drop here. And depending on the interface resistance, this value will change. Now the point is that when you look at the spin potential, you see, or rather let's think in up and down first, in terms of up and down. The point is the up and the down will experience different drops across that interface, because as we have seen in modules 1 and 2, the basic point, the basic phenomena that leads to all these effects we are talking about is the fact that when you have a magnetic contact, it has a different interface resistance for up channels and for down channels. That's really the basic phenomena. And so what happens is, if you looked at the up, it would be somewhere here. When you look at the potential for the up, and when you look at the potential for the down, it's somewhere here, some other value, you see. I guess I should be using red for this. So that red has a higher potential because there is less of a drop in the interface resistance, because the interface resistance is small. So this is higher than that. Now, on this side then, what you might expect is that this would gradually, so this difference is what you call mu s. That's the red and the blue. When you look at the difference between the two potentials, that's what you call the spin potential. And how does the spin potential vary with distance? Well, that's where, as I had argued, it obeys this basic equation, whose solutions have the form of exponentials. See? And so they will gradually decay. So when you look out here, what will happen is they won't stay constant, but will gradually go down out here. Okay. So way outside here, they'll gradually, somewhere way out there, they will eventually connect up, because eventually the spin potential will go to 0. But the distance it takes for it to go to 0, that's what's determined by the spin flip length, which is different for different materials. So whenever one is trying to do these experiments with spins on any material, of course, one of the first questions one looks into is that, what is the spin flip length? So if you're talking of copper, again, depending on the temperature, it could be hundreds of nanometers. Again, different materials could have very different numbers here. But that's one of the first parameters one looks into. Okay. Now, here what you can see is that if you are not too far away, that is, if you go too far away, of course, this difference will go to 0. But now if you're not too far away, there is a spin potential difference. There is this spin potential that you can measure. And ever since the late 1980s, there has actually been lots of experiments in different materials where people have measured this spin potential. And what I'll be trying to tell you, like the rest of this module, is exactly how people measure that. That's what we'll be talking about. Okay. And incidentally, on this part, this side, although we won't really be talking about this much, on this side also what will happen is the spin potential will gradually die out and join up with the, and just join up to a common value. That's what would happen on this side as well. But basically we'll be talking about this part, and the technical name is people call these non-local spin potentials. Non-local in the sense, you see the current flow is all around here. And ordinarily you think that this is outside the current path. There is really no action there, nothing important going on. But the measurements we'll be talking about are really all outside here. And so they call it a non-local measurement. And the way you do it is you put a magnet, put another magnet here, and you measure the voltage that that magnet floats to. See? And what we'll show is the following. What we'll argue is that if you look at the potential that you measure, mu, on this magnet, this measuring magnet, then you see if the magnet happens to be parallel to the injecting magnet, so that's what I'll call mu p. So that's what you measure if the magnet is a red one. So I'll put a red there. And if you look at the potential that you get when the magnet is in the blue, is a blue one, that's it has turned around, let me write that with mu AP. So it is that difference, you see? And that difference is equal to so if you are here and at this point, so let me call this point, say z equals, let's say we call this point z equals 0, and we call that point z equals L. So when you are here, what you'll measure will be whatever the spin potential happens to be at the point L, right there, see, times the polarization of that magnet. So we'll call this P2. 2 because, we now have these two magnets. This is one, that's another. So I'm calling this the magnet 1, calling that the magnet 2. So it's like the polarization of that magnet. Okay. So this is the result that we are trying to show. Okay. Now, if you actually want to relate what the measured quantity, if you want to relate this to measured quantities, then you see you have to relate this mu s at this point to the actual current in the circuit, because the current in the circuit is what you know experimentally. And there, I guess, there's a few steps involved which we won't go through in this lecture, but that's part of the tutorial lecture. There is a homework on this where in the tutorial I go through that part. And what it involves is how you relate this mu s to the current. So first thing is mu s at location L is actually the spin potential at location 0 times exponential minus z over, L over lambda SF. So this, of course, we expect from the solutions to the spin potential equation that I had mentioned before. The solutions have the form of exponentials. So the further you go, the spin potential dies out exponentially. Okay. So that's one. Now question is, what is mu s 0? Well, it is proportional to the current in the circuit. It's also proportional to the polarization of magnet 1. And that you might expect. The part that's not obvious and needs discussion, which is what the tutorial has, is that it's also proportional to, you see, this is like potential. And this, so dimensionally you want something like resistance here. I guess a Q and a resistance, and the correct resistance is RS, which is like the resistance of a channel whose length is lambda SF. And this part is, as I said, not obvious, but that's what's done in the tutorial. Okay. So let's forget this part. What we'll really talk about in the rest of this module is where this comes from, this part of it. Okay. Now the idea is something like this. That if I want to model how, wondering which would be the best place to do that. So let's look here. So if I'm trying to model what is the potential on this probe, new probe, say, and let us say this magnet happens to be parallel in the same direction. If I want to model that, the way you do it is, you could say that, well, from this channel, I have these two separate conductances, one due to up channels, one is due to the up interface, and the separate one for the down. Because as I said, all these phenomena we are talking about, they arise from the difference in resistances, interface resistances for the two channels. So you have an up channel and a down channel. This one has some mu up, and that one has some mu down. And they are connected to this mu p through the two conductances. And the question we are asking is, what is mu p in terms of mu up and mu down? And the way you do it is, you'd say, well, this thing is floating, so no current can flow. But there is a current here, and there is a current there. Because you could write this current as proportional to the difference between those two, that current as proportional to the difference between those two potentials. But the thing is, they must add up to 0, because the net current is 0. So that gives you the following condition then. That G up times this potential difference, which is mu up minus mu probe, plus G down times mu down minus mu probe. So this is the current in this up conductance, that's the current in the down conductance, and those two things must add up to 0. And then just one line of algebra and you'll get mu probe is equal to G up mu up plus G down mu down divided by G up plus G down. That's it. So this is what you'd measure with a parallel magnet. Now the spin potential, as I mentioned, actually depends on the difference between what a parallel magnet would measure and what an anti-parallel magnet would measure. So if I wanted what an anti-parallel magnet would measure, the point is that if I reverse that magnet, if I turn this around the other way, what will happen is it will reverse these two conductances. That is, what used to be the up conductance will now become the down conductance, and what used to be the down conductance will now become the up conductance. So what it means is the mu AP would be given by exactly the same equation, except that instead of G up, I'll now have a G down. Let me find a better pen. Yeah, G down mu up plus G up mu down divided by G up plus G down. So all I did was took the expression I had and reversed G up and G down. Now what I can do easily is find the difference between the two. So in fact, let me do it over here. I don't need this picture anymore. I'm just finishing up. So what you get then is mu p minus mu AP is equal to, so you're taking mu p minus mu AP, and what you'll get is G up minus G down divided by G up plus G down times mu up minus mu down. See? And this is the basic result. So, and mu up minus mu down, of course, is just the spin potential at the location of the probe. So that's mu SL. And this quantity, this difference of the conductances divided by the sum of the conductances, which is also equal to the difference of the resistances divided by the sum of the resistances, same thing. And this is what is the polarization of magnet 2. So that's the basic point I was trying to prove, as I stated before, that what you'd measure by reversing that magnet outside the current path is the spin potential at that location. And lots of these measurements have been done. And one of the things, I'll bring this up a little later again, like in the last module, when I'll try to explain some of the subtle aspects that I've glossed over here. What is very interesting about spin is that there's a whole set of properties that you can understand in fairly simple terms just by saying there's a red type and a blue type. And charge means the sum of the two, and spin is like the difference between the two. On the other hand, there's a few things that are not quite, cannot be understood this way and needs a more advanced point of view. And that's what I'll try to talk about in the last module. But what we'll do in the next two modules, though, is we'll talk about why, try to get a better understanding of what gives rise to the difference in the interface resistance. So far we have said, assume there's a difference in interface resistance, and we looked at the consequences. But now what we'll talk about is what gives rise to the difference, and also this very important phenomena of spin torque. That is what now has been demonstrated is that these spin currents can actually even turn a magnet. That is, what was first demonstrated is that magnets can inject spins and give rise to spin currents. And it sort of completes the loop. Now people have shown that spins can be used to turn magnets.